Good morning, classmates. Good morning, teachers. Good morning, ma'am. We are the reporters in hypothesis testing, drawing inferences from sample data, and I am assigned to report to you the test concerning one population mean, the z-test, and the t-test. And I am also assigned to report to you the p-value approach. Okay, let's start. Hypothesis testing and drawing inferences from sample data. What is hypothesis test? It's a process that uses sample statistic to test a claim about the value of population parameter. Example, if a manufacturer of rechargeable batteries claims that the batteries they produce are good for an average of at least 1,000 charges, a sample would be taken to test this claim. Or for example, we have to claim if it is correct or incorrect that the manufacturer of the said rechargeable batteries um, claims that their batteries that they have produced can has the average charge of 1,000. A verbal statement or claim about a population parameter is called a statistical hypothesis. To test the average of 1,000 hours, a pair of hypotheses are stated, one that represents the claim and the other its complement. One with this hypothesis is false and the other must be true. Since we have two opposing claims, so one of it must be true and one of it is rather false. Hypothesis testing is used to assess the plausibility of a hypothesis by using sample data. The test provides evidence concerning the plausibility of the hypothesis given the data. Statistical analysis tests a hypothesis by measuring and examining a random sample of the population being analyzed. Stating a hypothesis, we have a null hypothesis representing H sub 0 or H naught is a statistical hypothesis that contains a statement of equality such as not less than or equal or not greater than. Those are the symbols in the null hypothesis. And we have the alternative hypothesis represented as H sub A. Is the complement of the null hypothesis. It is a statement that must be true if sub 0 is false and contains a statement of inequality such as greater than, in unequal, or less than. To write the null and alternative hypothesis, translate the claim made by the population parameter from a verbal statement to a mathematical statement. Example, write the claim as mathematical sentence, state the null and alternative hypothesis, and identify which represents the claim. Example, manufacturer claims that its rechargeable batteries have an average life of at least 1,000 charges. So, we have here the clue in the sentence, average life of at least 1,000 charges. We have here the 1,000 as the condition of equality. The null hypothesis is 1,000 or the claim, and we have the alternative hypothesis 1,000 also, which is the complement of the null hypothesis. Stating this is how to state a hypothesis. Example, write the claim as a mathematical sentence, state the null and the alternative hypothesis, and identify which represents the claim. Example, Statesville College claims that 94% of their graduates find employment within 6 months of graduation. We have here 94% as the condition of equality. 94% into its decimal form. We have 0.94 as the claim in the null hypothesis, and in the alternative hypothesis, we also have 0.94. I p-value, or the probability, is not equal to 0.94, the complement of the null hypothesis. Test concerning one population mean, or the z-test. The one sample z-test is used to test whether the mean of a population is greater than, less than, or not equal to a specific value, because the standard normal distribution is used to calculate critical values for the test. This test is often called the one sample z-test. How z-test is used in testing hypotheses. Z-test is a statistical test to determine whether two population means are different when the variances are known and the sample size is large. Z-test is a hypothesis test in which the z-statistic follows a normal distribution. A z-statistic, or z-score, is a number representing the result from the z-test. We have here the normal, or the t-distribution. We have to determine or identify, are both sample sizes are at least 30. This is an example. If yes, use the z-test, and if no, are both populations normally distributed? If no, you cannot use the z-test or the t-test. Are both population standard deviation known? Then, if yes, use the z-test. And if no, are the population variances equal? And if no, use the t-test with that equation, or that formula. And if yes, use the t-test with that formula also. T-test for the difference between means. To perform a two-sample hypothesis test with independent samples, the difference between each data pair is first found. The D is equals to x sub 1 minus x sub 2, difference between entries for a data pair. The statistic is the mean of these differences, where in D is equals to summation of D over N, when mean of the difference between paired data entries in the dependent samples. Three conditions are required to conduct the test. First, the samples must be randomly selected. So, since we already have the samples, they must be selected randomly, and the samples must be dependent. So, when we say dependent, it must be paired. Both populations must be normally distributed. If these conditions are met, the sampling distribution is approximated by a t-distribution with n minus 1 degrees of freedom, where n is the number of data pairs. N is represented by the data pairs. This is a representation of the graph of the null hypothesis, and the t-test of the null hypothesis and alternative hypothesis. T-test for the difference between means. The following symbols are used for the t-test. N is the number of pairs of data, as what I have said earlier. D is the difference between entries for a data pair. We have D is equals x sub 1 minus x sub 2. And the hypothesized mean of the difference of paired data in the population, and the mean of the differences between the paired data entries in the dependent samples. D is equals to summation of D over N. And we have the SD, or the standard deviation of the differences between the paired data entries and the dependent samples. These are in the lower part is the formula. T-test for the difference between means. A t-test can be used to test the difference of two population means when a sample is randomly selected from each population. The requirements for performing the test are that each population must be normal and each member of the first sample must be paired with a member of the second sample. The test statistic is D is equals to summation of D over N, and the standardized test statistic is T is equals to D minus the U and D over standard deviation over summation square root of N. The degrees of freedom are degrees of freedom is equals to N minus 1. Using the t-test for the difference between means or the dependent samples, we have here in words and in symbols. State the claim mathematically, identify the null and alternative hypothesis. This is the symbol on how to state the H sub 0 and H sub A. Specify the level of significance we have identified as A, or the level of significance. Identify the degrees of freedom and sketch the sampling distribution, or the D and F is equals to N minus 1. D and F is representation of degrees of freedom. Determine the critical values, and using a two-sample t-test for the difference between means, small independent samples in words and in symbols. We have the fifth one, determine the rejection region or regions, calculate and use a table. Standardized test statistic. For the eighth, make a decision to reject or fail to reject the null hypothesis. Since you interpreted already, so you can now interpret or determine whether it is rejected or failed. 9. Interpret the decision in the context of the original claim. Since there is a claim happened and you have calculated already, and then you can now interpret or determine whether it is rejected or failed. Example. We have here an example. A reading center claims that students will perform better on a standardized reading test after going through the reading course offered by their center. The table shows below the reading scores of 6 students before and after the course. At A, or the significance level is 0.05. Is there enough evidence to conclude that the students' scores after the course are better than the scores before the course? Okay, let's check it out. Student 1, score before the course is 85 and after is 88. So there is an improvement or an increase of the score. While student 2 before is 96 and it decreases to 85. So there is a decrease happens, so no improvement. Rather, it is it lowers its performance. And in student 3, it increases 70 to 89. In student 4, 76 to 86, it increases also. In student 5, we have 81 to 92, it increases also. And as well as in student 6, it's 78 to 89. So 5 of the students has an improvement since their scores from before is increases to the after result compared to student number 2 wherein its result is decreased. So that is how to represent its claim. Example, the degrees of freedom is 6 minus 1 equals 5 since the n or the number of students is 6 and the degrees of freedom is represented by the n minus 1. So, there are 6 students minus 1 is equals to 5. So, we have here 0.05. We have the score before and after. The D is represented below in the score after, and it is multiplied by itself, since D square to is D the power of 2, and that is the result. In D we have negative 43, and D in the power of 2 is 833. So what we'll do next is to get the standard deviation. We have here the formula as you see in the screen. So we have, since we get already there is 6 students, and 833 is the result of D to the power of 2 minus 1, 849 over 6. 6 is the number of students, and the 5 is the n minus 1, and is equals to the square root of 104.967 is 10.245. If the null hypothesis is true, a p-value or probability value of the hypothesis test is the probability of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample data. The p-value of hypothesis test depends on the nature of the test. These are 3 types of hypothesis test: a left, right, or two-tailed test. The type of test depends on the region of the sampling distribution that favors a rejection of H sub 0 or the null hypothesis. This region is indicated by the alternative hypothesis. Left-tailed test. If the alternative hypothesis contains less than inequality symbol, the hypothesis test is a left-tailed test. That is a representation of a left-tailed test. There is a less than inequality symbol, or it is in the region of the negative in the graph, wherein P is the area to the left of the test statistic. Next is we have the right-tailed test. If the alternative hypothesis contains the greater than symbol, the hypothesis test is right-tailed test, as what you have seen here in the graph in the positive region, wherein P is the area to the right of the test statistic. That is the representation of right-tailed test. Belong to the right side, or wherein the positive integers indicated. We have the two-tailed test. If the alternative hypothesis contains the not equal to symbol, or this not equal to the symbol is shown, the hypothesis test is a two-nailed test. In a two-nailed test, each tail has an area of P. This is its representation. That is the graph or the representation of a two-nailed test. We have an not equal to symbol, since there is unequal shaded parts in the two opposite region, in the positive and in the negative, in the right and in the left tailed. Identifying types of tests. For each claim, state null hypothesis and alternative hypothesis. Then determine whether the hypothesis test is left-tailed, right-tailed, or two-tailed test. Example, a cigarette manufacturer claims that less than 1/8 of the U.S. adult population smokes cigarettes, wherein the null hypothesis P is not is not greater than 0.125, and the Alternative hypothesis where probability less than 0.125 is the claim or the left-tailed test. Example number 2. A local telephone company claims that the average length of phone call is 8 minutes. So we have the claim 8 as the null hypothesis, and we have the representation of the alternative hypothesis or the not equal to 8. So since we have a not equal to symbol, so this is a representation or an example of a two-nailed test, correct? Steps for hypothesis testing. State the claim mathematically and verbally. Identify the null and the alternative hypothesis. Second, specify the level of significance. We have the representation A is equals to unknown. Determine the standardized sampling distribution and draw its graph as what you have seen. Calculate the test statistic and its standardized value. Add it to your sketch. Since you already have the value, then you can now start your sketch and putting a value on it. Next, fifth is find the p-value. Use the following decision rule. Is the p-value less than or equal to the level of significance? If yes, reject null hypothesis, and if no, fail to reject null hypothesis. Seventh, write a statement to interpret the decision in the context of the original claim. These steps apply to left-tailed, right-tailed, and two-nailed tests. These can be applied in all of the areas in identifying tests or in identifying hypothesis testing. Using p-values to make a decision. Decision rule based on p-value. To use a p-value to make a conclusion in hypothesis test, compare the p-value with A or the significant level of significance. If P is not less than the level of significance or A, then reject the null hypothesis. If P is greater than the level of significance, then fail to reject null hypothesis or H sub 0. Recall that when the sample size is at least 30, the sampling distribution of the sample mean is normal. Example, the p-value for a hypothesis test is P is equal to 0.0256. What is your decision if the level of significance is A, 0.05, and the second one is 0.01? For the first one, 0.05 in sample letter A, because 0.0256 is less than 0.05, you should reject the null hypothesis. Because 0.0256 is greater than 0.01, you should fail to reject the null hypothesis. That is a clear representation of the two, or the differences between the two. Finding the p-value. After determining the hypothesis test's standardized test statistic and the test statistics corresponding area, do one of the following to find the p-value. For A, for a left-tailed test, P is equals to area in left tail. For a right-tailed test, P is equals to area in right tail. And for a two-tailed test, P is equals to area in tail of test statistics. Since it's a two-tailed test, so there is a duplication happen or the representation of 2. Example, test statistic for a right-tailed test is Z is equals to 1.56. Find the p-value. And now to find the p-value and determine if it is a right or left-tailed test. Since 1.56 is the area of the right of Z is equals 1.56 is 1 negative 0.9406 is 0.90594. The p-value 0.594 is equals to 1.56. So, it is a right-tailed test. Another example. The test statistic for a two-tailed test is z is equals to negative 2.63. Find the p-value. That is a representation. Since it is a negative 2.63, it is a two-tailed test. The area of the left of z is equals to negative 2.63 is 0.043. And the value is 2, close open parenthesis, 0.0043 is equals to 0.0086. The z-test for the mean is a statistical test for a population mean. The z-test can be used when the population is normal and is known for any population when the sample size n is at least 30. The test statistic is the sample mean, and the standardized test statistic is z. That is the formula, as what you have seen in the screen. When n is not greater than 30, the sample standard deviation S can be substituted for an O. Using p-values or z-test for a mean, in words and in symbols, these are those. Same as what I have presented earlier. State the claim mathematically and verbally. Identify null and alternative hypothesis. We have state H sub 0 and H sub A. Specify the level of significance. We have to identify the A or the level of significance. Determine the standardized test statistic, or if it is left-tailed, right-tailed, or two-tailed test. Then find the area that corresponds to Z. Then after that, you can now be able to graph or to make a representation of your graph if it is a right-tailed, left-tailed, or two-tailed test. Using p-values for a test for a mean, we have the continuation. Find the p-value for a left-tailed test, area in left tail, as well as in right-tailed test, area in the right. And in the two-tailed test, both areas of the graph or the region. Then, sixth one, make a decision to reject or fail to reject the null hypothesis. As what I have said, reject null hypothesis if p-value is less than or equal to the level of significance, and otherwise fail to reject null hypothesis. Then after that, since you will be able to determine now, then if it is left or right-tailed or two-tailed test, then you cannot be able to interpret the decision in the context of the original claim, if it is rejected or failed. Next example is we have hypothesis testing with p-values. Example, a manufacturer claims that its rechargeable batteries are good for an average of more than 1,000 charges. A random sample of 100 batteries has a mean life of 1002 charges and standard deviation of 14. Is there enough evidence to support this claim at level of significance is equal to 0.01? Okay, let's see. Null hypothesis is not less than 1,000, and alternative hypothesis we have greater than 1,000, or this is the claim since the battery charges is 1,000. The level of significance since is 0 equals to 0.01 as what is stated in the sentence or in the problem. The standardized test statistic is, this is now the representation. The Z is equals to x, that is the formula, is equals to 1002 as the charges, or the standard, as the mean life charges of the battery, is equals minus 1000 charges is equals to 14 as the standard deviation over square root of 100, or the random sample. We have the result 1.43. Since we come up to 1.43, we can now have there's some representation of a graph over 1.43 in the z-test. The area of the right of to the right of z is equals to 1.43 is probability of p 0.0764. P value is greater than the level of significance z 0.01, so the result is fail to reject null hypothesis. At the 1% level of significance, there is not enough evidence to support the claim that the rechargeable battery has an average life of at least 1000 charges. So it is failed to reject, a rejection region, or the critical group or region of the sampling distribution, is the range of values for which the null hypothesis is not probable. If a test statistic falls in this region, the null hypothesis is rejected. Then a critical value is z. Null hypothesis sub-zero. Separates the rejection region of the non-rejection region. Example, find the critical value in the rejection region for a right tail test with level of significance 0 is equals to 0.01. This is the representation. The rejection region is to the right of z is equals to 2.575. So, and for the critical values in a t-distribution, this is how to find the critical values in t-distribution. Identify the level of significance, or the A. Identify the degrees of freedom, or df, is equals to n minus 1. That's what I have presented earlier. That is 1. Same. The same also. Another, for the information of everybody, for left-tailed, use one tail column with a negative sign, and for the right tail, always remember that it is in the positive side. And for the two-tailed, it is in the both side, negative and in the positive side. Example, find the critical value of t sub-zero, or the null hypothesis, for a right-tailed test given the level of significance 0.01 and n is equals to 24. The degrees of freedom, or df, n minus 1 is 24 minus 1 is 23. We have the 23. To find the critical value, use the table 5 with degrees of freedom 23 and 0.25, 0.01 as the level of significance in the one tail column. Because the test is a right-tailed test, the critical value is positive. That's what I have said. If it is right-tailed test, it is a positive. And for the t is 2.500. Same also. The t-test for the mean is a statistical test for a population mean. The t-test can be used when the population is normal or nearly normal, is known, and n is less than 30. This is the formula. Next, the degrees of freedom d and f is equals n minus 1. And for further understanding, I have here a short video presentation on how to get the z-test and the t-test. This is a video presentation on how to get or to solve the z-test and the t-test for your further clarification or further understanding.
Let's look into testing a hypothesis about the population mean when sampling from a normally distributed population. And the question I'm going to look at here is, should we use a t-test or a z-test? Suppose we are sampling from a normally distributed population, and we wish to test the null hypothesis that the population mean is equal to some hypothesized value mu naught. If the population standard deviation sigma is known, then we would use this z-test statistic. And if the null hypothesis is true, this z-test statistic has the standard normal distribution. But in the real world, it would be very rare that we would know the value of sigma. And so we replace the value of sigma, the population standard deviation, with our sample standard deviation. And we get a very similar test statistic, but something fundamental has changed in the underlying mathematics. And this t statistic does not have the standard normal distribution. If the null hypothesis is true, this test statistic will have a t distribution with n-1 degrees of freedom. I've looked at the similarities and differences between the t distribution and the standard normal distribution elsewhere, but let's do a brief recap. The curve in white is the standard normal distribution, and the curve in red is a t distribution with 2 degrees of freedom. Both the standard normal distribution and the t distribution are symmetric about 0 and bell-shaped, but the t distribution has heavier tails and a lower peak. Here I have a t distribution with 2 degrees of freedom, but as those degrees of freedom increase, the t distribution tends toward the standard normal distribution. So let's see what happens when we increase those degrees of freedom. Here's a t distribution with 10 degrees of freedom, with 15, with 20, and that t distribution is getting closer and closer to the standard normal. The degrees of freedom are a function of the sample size. Here, the degrees of freedom are n-1. And so if we have a large sample size, the degrees of freedom will be large, and the t distribution will be very close to the standard normal distribution. And so some sources say that if the sample size is greater than 30, just forget all about that t distribution and just use the standard normal distribution. But if you are taking statistics with me, forget you ever heard such a thing. And many others feel the same way as well. If it is truly a t statistic, we should be using the t distribution. Let's look at a quick example to illustrate the differences. Suppose we are sampling 35 values from a normally distributed population, and we wish to test the null hypothesis that the population mean is 100 against a two-sided alternative. The sample mean and sample standard deviation are found to be 104 and 12 respectively. Since we have a sample standard deviation, our standard deviation is calculated based on sample data, we should be using the t statistic. And our t statistic is x bar minus mu naught over s over the square root of n. And in this case, that's 104 minus the hypothesized value of 100 over 12 over the square root of 35. And that works out to 1.972. Here our sample size is 35, and so the degrees of freedom, being n-1, are 34 in this case. Our alternative hypothesis is two-sided, and so the p-value is going to be the area in the tail beyond this test statistic doubled under a t distribution with 34 degrees of freedom. Here I've plotted out in white a standard normal distribution, and in red a t distribution with 34 degrees of freedom. They look very close, but you may still be able to tell that the t-distribution has slightly heavier tails and a lower peak. Let's split those up and find the p-value. Here's our t-distribution with 34 degrees of freedom, and the observed value of our test statistic was 1.972. And our alternative hypothesis was two-sided, so the p-value is this area in the tail beyond the test statistic doubled. And if we went to computer software, we would see that the correct p-value here, using the t-distribution, is 0.0568. Had we said, well, our sample size is greater than 30, so let's forget about the t-distribution and go to the standard normal distribution, and we put in the value of our test statistic there at 1.972, we got the area in the tail here beyond the test statistic and doubled it, we would have found the incorrect p-value based on the standard normal distribution of 0.0486. Now that's a little bit smaller than the correct p-value based on the t-distribution. Granted, they're fairly close, but I would say that that difference that we see is a meaningful difference. Here, if we used the standard normal distribution to find the p-value, we would be overstating the evidence against the null hypothesis. This difference will get smaller and smaller as the sample size gets larger and larger, but we might as well use the correct distribution. And so I suggest, and it's a point of view shared by many others, that if we have a t-statistic, we should find the p-value based on the t-distribution, and not simply say, well, we have a large enough sample size, so the standard normal distribution is good enough. On a final note, in practice we carry out the analysis using software, and here's the output for the example. Regardless of whether there are 2 degrees of freedom, 34 degrees of freedom, or 1,000,000 degrees of freedom, if the test statistic is calculated using the sample standard deviation, the software will find the p-value using the t-distribution with the appropriate degrees of freedom.
Now, I'll show to you a short video presentation on how to understand the p-value or understanding the p-value.
Understanding the p-value. One of the most important concepts in statistics is the meaning of the p-value. Whenever we use Excel or other computer packages to analyze data, one of the key outputs is the p-value, or sig. In formal terms, the p-value is the probability that, if the null hypothesis were true, sampling variation would produce an estimate that is further away from the hypothesized value than our data estimate. In less formal terms, the p-value tells us how likely it is to get a result like this if the null hypothesis is true. We will now go through this step by step with an example. Helen sells choconutties. Recently, she has received complaints that the choconutties have fewer peanuts in them than they are supposed to. The packet says that each 200-gram packet of choconutties contains 70 grams of peanuts or more. Helen can't open up all the packets to check, as then she wouldn't be able to sell any. So she decides to use a statistical test on a sample of the packets. The null hypothesis, often called H0, is the thing we are trying to provide evidence against. For Helen, the null hypothesis is that the choconutties are as they should be. The mean or average weight of peanuts in the packet is 70 grams. The alternative hypothesis, called H1 or HA, is what we're trying to prove. The customers have complained that the weight of peanuts is less than what it should be. So the alternative hypothesis is that the average weight of peanuts is less than 70 grams. Helen decides to use a significance level of 0.05. If the p-value is lower than this, she will reject the null hypothesis. Decided on her hypotheses and on the significance level, Helen takes a random sample of 20 packets from her current stock of 400 packets. She melts down the choconutties and weighs the peanuts from each packet. If all of the values were lower than 70 grams, with a mean of 30 grams for instance, it would be quite obvious that the bars did not have the required number of peanuts. It is very unlikely that you will get 20 packets with a mean of 30 grams if the overall mean of all the packets in the population is 70 grams. Conversely, if all the values of the 20 packets were much higher than 70 grams, it would be obvious that there were enough peanuts and that there was nothing to complain about. However, in this case, the 20 packets contain the following weights of peanuts, and the mean is 0.7 grams. This caused Helen to ask herself, does this provide enough evidence that the bars are short of peanuts, or could this result just be from luck? She asked her brother to use Excel to find the p-value for this data, comparing with a mean of 70 grams. The p-value is 0.18. Judging from the data that we have, there is an 18% chance of getting a mean as low as this or lower if there is nothing wrong with the bars. That is, if the null hypothesis is true and the mean weight of nuts is 70 grams or more. This p-value of 0.18 does not provide enough evidence to reject the null hypothesis. In this case, Helen does not have evidence to say that the bars are short of peanuts. This is a relief. The smaller the p-value is, the less likely it is that the result we got was simply a result of luck. If the p-value had turned out to be very small, we then would say that the result was significantly different from 70 grams. In general, we start by saying that the null hypothesis is true. We take a sample and get a statistic. We work out how likely it is to get a statistic like this if the null hypothesis is true. This is the p-value. If the p-value is really small, then our original idea must have been wrong, so we reject the null hypothesis. P is low, null must go. A small p-value indicates a significant result. The smaller the p-value is, the more evidence we have that the null hypothesis is probably wrong. If the p-value is large, then our original idea is probably correct. We do not reject the null hypothesis. This is called a non-significant result. The p-value tells us whether we have evidence from the sample that there is an effect in the population. A p-value less than 0.05 means that we have evidence of an effect. A p-value of more than 0.05 means that there is no evidence of an effect. Sometimes a significance level different from 0.05 is used, but 0.05 is the most common one. Disclaimer. This video uses plain language to get difficult ideas across. Some terminology might be viewed as incorrect by a rigorous statistician.
That's all about my report. I hope you all understand, and God bless, and thank you for listening, teachers, classmates, and Mamai. Thank you for listening, and God bless, and God bless, and stay safe for everyone, and break a leg for our final exam. Thank you.